So, let us see what the so called asymptotic Bode plots look like. These are approximations to the exact frequency response, and more than that, it provides a quick method of sketching the frequency response. And as I told you earlier, it gives you a good qualitative idea of what is going to happen. It is not a very good quantitative method. It is not a substitute for exact calculations of gain and phase shift. So, with this understanding, let us go ahead. So, suppose we have a numerator factor which, because of it being a 0, we write as s minus z, and remember that I am looking at the case when the z is a real number, that is, this is a real 0. The 0 may be in the left half plane or it may be in the right half plane. So, I am assuming that z is not 0. In this case, when we look at the frequency response part corresponding to this term, we replace s by j omega. So, I have j omega minus z, and the modulus of that is the gain or the absolute gain, as one might call it, and 20 log to the base 10 of that is the dB gain, and the angle or the argument of that is the phase shift, right. Now, if we look at the gain first, that is the magnitude, and the dB gain first, then as we saw earlier, there are two approximations. One is as omega tends to 0, the gain approaches the low frequency gain, so called low frequency or DC gain, which is given by 20 log to the base 10 of the absolute value of the real number z. Of course, depending on the value of this real number z, if it is less than 1, then this will be negative. If it is greater than 1, it will be positive. If z just happens to be 1, for example, there is a 0 at plus 1 or minus 1, then this will be equal to 0. So, this will be some number, and remember the unit for this is said to be decibels. So, this is the DC gain or the limit as omega tends to 0. Now, on the other hand, we can look at the case when omega tends to infinity, and that is when from j omega minus z we can ignore z, and all we are left with is omega, and therefore 20 log to the base 10 of omega is what we get as the dB gain. And therefore, if this is plotted against log 10 to the base of omega, and I said that you can think of log 10 to the base of omega as a new variable, let us call it u, then this is simply 20u, and therefore the plot of the dB gain, this is the dB gain versus u, will be a straight line. It will be a straight line passing through the origin of u plane or u equal to 0, and it will have a slope of 20. And remember, now we are looking at u, which is logarithm to the base 10 of omega. So, when omega is changed by a factor of 10, that is, you multiply or divide it by a factor of 10, u changes by plus 1 or minus 1. Therefore, the dB gain will change by plus or minus 20 dB according as we increase or decrease omega, and therefore this slope is referred to as 20 dB per decade. That is, for a change in frequency by a factor of 10, there will be a change in the decibel gain of 20 decibels. Because we are looking at the 0, when the frequency increases, the gain increases, when the frequency decreases, the gain decreases. For every decade change, and remember, this decade change does not mean an amount of 10 hertz, but it is a factor of 10. So, 1 hertz to 10 hertz, 1 hertz to 10 hertz, that is a difference of 9 hertz. But it is a difference by a factor of, or it is a multiplication by a factor of 10. So, 10 hertz is said to be 1 hertz, 1 decade above 1 hertz. Similarly, 10 hertz to 100 hertz, the difference is 90 hertz, but the relationship in terms of ratio is by a factor of 10. So, we say that 100 hertz is 1 decade higher than 10 hertz. And now, what therefore this says is that the gain, when the frequency is changed from 1 hertz to 10 hertz, the decibel gain change will be by 20 decibels. When we change from 10 hertz to 100 hertz, it will also be by the same amount, namely 20 decibels. So, we speak of the slope of this line or the change in dB gain as related to the frequency, but frequency expressed logarithmically, log to the base 10 of omega, as 20 decibels per decade. And as I told you earlier, in music, one talks about not decade but octave, that is a doubling of frequency. So, if omega is changed by a factor of 2, not by 2 hertz, but by a factor of 2, that is, if omega was 1 hertz, now we consider 2 hertz, or if it was 100 hertz, we consider 200 hertz. So, there is a change in omega by a factor of 2, then because log to the base 10 of 2 is how much? Is about 0.3. Therefore, the change in the dB gain will be about 6 dB, and therefore, the same slope is also referred to as 6 dB per octave. So, 20 dB per decade and 6 dB per octave are the same rate of change of decibel gain with change in frequency, but change in frequency is talked about in logarithmic terms, that is in terms of multiplication by a factor and not by a difference of a certain amount. Okay. So, with this then the graph of dB gain versus u will be a straight line, but it will be a straight line passing through the origin corresponding to u equal to 0. Now, unfortunately u equal to 0, or I should not say unfortunately, you have to keep in mind that u equal to 0 is not 0 frequency, because u is what? U is log to the base 10 of omega. So, u equal to 0 corresponds to omega equal to 1. Now, depending on how you are plotting the graph, whether you are plotting it in terms of hertz, that is actual cycles per second frequency as such, or you are plotting in terms of the corresponding angular velocity omega, which is 2 pi f, and remember we have to substitute s by omega, not s by f. So, if you want to put f there, then you have to replace s by 2 pi f. So, accordingly then one may plot radians per second or hertz, that is cycles per second. So, accordingly the u equal to 0, u equal to 0 will correspond to omega equal to 1, and therefore 1 radians per second, or if you want in terms of hertz, then this will correspond to 1 by 2 pi hertz. So, when the angular velocity is 1 radian per second or the corresponding frequency is 1 by 2 pi hertz, this high frequency approximation, as it is called, will give you a value of 0 dB, and therefore it will pass through the point 0 dB and omega equal to 1 radian per second. So, for a moment if I just work with omega rather than f on the horizontal axis, then let us say here is my horizontal axis, and I am going to put here both omega as well as u. Although when we use the semi-logarithmic paper, the graduation along the horizontal axis is such that one should think of not omega but u. If you think of equal increments, equal movement along the horizontal axis correspond to equal changes in u and correspond to multiplication of omega by the same factor. So, let us say on this graph paper I have put down here a point which corresponds to omega equal to 1, and on the paper you do label it as omega equal to 1, although in terms of u it is equal to u equal to 0. Then here is the point, the next cycle or decade, this is omega equal to 10 and this will correspond to u equal to 1, and let us say the vertical scale is such that this line corresponds to 0 dB and this line corresponds to 20 dB. Then the high frequency approximation or high frequency asymptote, as it is called, is a straight line passing through this point when omega equal to 1, u equal to 0, and having a slope of 20 dB per decade. Therefore, if I move from omega equal to 1 to omega equal to 10, this is a change of 1 decade by a factor of 10. There should be a gain, a change in dB gain by an amount 20, and therefore the line will look like this. So, this will be the high frequency asymptote, that is, this will be more and more accurate as omega increases. So, the graph of the gain as a function of frequency or logarithm of frequency is of this kind at high frequencies. On the other hand, at low frequencies it tends to a constant, and therefore it is just a line. Now, one can check that, and now I am not going to show the scales. So, I am just going to draw the curves or the approximations without showing the scale. So, let us say here is the low frequency approximation, which is just a horizontal straight line because the dB gain is constant equal to the DC gain. Here is the high frequency approximation, which is intersecting this line with this. Then what is the value of omega corresponding to this point. Now, this is the low frequency approximation, this is the high frequency approximation. So, what we mean is, as omega tends to 0, we are getting closer and closer to this curve, and as omega increases to a large value, we are getting closer and closer to this curve. So, what is the actual shape of the curve modulus of j omega minus z, with z real? What is the actual shape of the curve? Now, a little bit of a calculation will show you that the following is the shape of the curve. The curve looks like this. So, it lies above this DC asymptote, it lies above the high frequency asymptote, and what is the point where the two asymptotes intersect? As for an obvious reason, this point or the corresponding frequency or omega is referred to as the corner frequency, because if you think of this and this as an approximation, then this approximation is not given by a single straight line, but is given by a portion of a straight line and another straight line, and there is a corner here, and this is called a corner frequency. You can show that this corner frequency is exactly the absolute value of this number z. So, wherever the 0 is, if the 0 is at minus 2, it is in the left half plane, its absolute value of minus 2, therefore 2. So, 2 radians per second will be the corner frequency. I am referring it to frequency, but it is actually the value of omega. So, if you are thinking of real frequency which is in hertz, then this will have to be divided by 2 pi. So, this is the corner frequency, alright. It corresponds to the absolute value of z. If z is plus 1, let us say there is a 0 in the right half plane, then absolute value of plus 1 is of course plus 1, and therefore it is still the same thing, namely 1 radians per second. Now, obviously there is an error here, because the actual curve is like this, the asymptotic curve we are at the corner. So, what is the amount of this error? Now, again I will leave it to you and do it on your own, do not look at the book. Look at this expression mod j omega minus z and put omega equal to absolute value of z. You can take a numerical example if you wish, and then find out what is the difference between this value, which is the DC gain, and the exact value at the corner frequency. Then one can show that this is very close to 3 dB. So, in other words, this asymptotic approximation, which is very good at low frequencies and quite good at high frequencies, is in error at this corner frequency by an amount of 3 dBs. So, what one can do is one can draw these two asymptotes and then choose a point 3 dB above this corner point. Then you have this point on the curve and you have these two asymptotes, and I am assuming you are good at engineering drawing, then you should be able to draw a smooth curve of this kind. It should not intersect this asymptote, it should not intersect this asymptote, it should lie above the asymptotes, and it should pass through this point which is 3 dB above the corner frequency. In fact, one can get 2 more points on this curve, that is, if you take a frequency which is 1 octave below this frequency, that is, whatever this frequency is, the frequency which is 1/2 of that. If you go 1 octave below, then the error or the difference is just 1 dB. And if you go 1 octave above, that is, take a frequency which is double the corner frequency, then here also the error is just 1 dB. So, if you want to plot this approximation in such a way that it is a little better, then you choose this point 3 dB above the corner frequency, choose this point 1 dB above a frequency which is 1 octave below the corner frequency, that is 1/2 of the corner frequency. Then take a frequency which is double the corner frequency, that is 1 octave above the corner frequency, and go 1 dB above this asymptote. Then you will have one point here at the corner frequency, one point here which is 1 octave below, another point here which is 1 octave above. Now you have 3 points to which through pass the curve in such a way that these are the 2 asymptotes, and so one should be good enough at engineering drawing to draw this smooth kind of curve. And this is a fairly good approximation to the actual variation of gain with frequency. Now, Bode's idea was not just to draw such a curve, but then was to see something more, which I will come to very quickly. Now, this was for a 0. this was for one zero. Now, the transfer function may have several zeros. So, then what happens? As we saw, the reason for taking logarithm of the modulus was because the modulus was the modulus of a product of numerator terms divided by a product of denominator terms. Taking logarithm converts the product into sum, converts the division into difference. So, essentially what we have is, if we have 1 0, then we have this approximation. The 1 0 will correspond to one corner frequency. If I have another 0, I will have another approximation with a different corner frequency, and so on. Now, what happens in the case of a pole is just a little different, but of course the difference is important. So, I am now looking at a factor like s minus p, which however is in the denominator. And so, correspondingly I have in the denominator j omega minus p, where p is the location of the pole, and the pole may be in the left half plane or in the right half plane. I am assuming that p is not 0 once again, that is, there is no imaginary axis pole or an imaginary axis 0, right. Then what happens? The only difference is, because now this is in the denominator, when I take 20 log to the base 10, I get a minus sign. So, once again we can have the low frequency gain as omega tends to 0, which will be given by minus 20 log to the base 10 of absolute value of the pole value, minus 20 minus sign because it is in the denominator, and when I take log, if something is in the denominator, logarithm gives you a minus sign. So, minus sign here. Similarly, the asymptote as omega tends to infinity will be what? It will be given by minus 20 log to the base 10 of omega. So, if you think of it as a function of log 10 of omega, then again it is given by a straight line, but the slope of the straight line is now minus 20, or it has a negative slope, and as a result therefore, if I show the low frequency or DC asymptote and the high frequency asymptote, then the DC asymptote once again will be a horizontal line. The high frequency asymptote will be now sloping downwards, and the downward slope therefore is shown as minus 20 dB per decade or minus 6 dB per octave. For every multiplication or increase in frequency by a factor of 10, there will be a reduction in gain by 20 dB. The point of intersection of these two asymptotes is, as you can expect, absolute value of p, where p is the location of the pole. So, if there is a pole at minus 2, then it will be absolute value of minus 2, that is 2 radians per second. If the pole is in the right half plane, say p is equal to 2, then an absolute value of 2 is just the same as 2. So, it is again 2 radians per second. So, the point of intersection is not a negative frequency or a negative value of omega, it is the absolute value of the location of the pole. So, this is the point of intersection. So, this is the corner frequency corresponding to a pole. Now, what about the actual curve? In the case of the 0, the actual curve, as I told you, was above the asymptotic approximation. So, in the case, this is the case of the 0, the asymptotic approximation is below the actual. In the case of a pole, we expect just the opposite to happen. So, the asymptotic curve is going to be above the actual, and this time at the corner frequency, therefore, once again the error will be 3 dB, but the actual will be 3 dB below. 1 octave above the corner frequency, the error will be just 1 dB below, and 1 octave above, the error will also be 1 dB. The actual curve is below. Now, I have 3 points and I know that these are the asymptotes. So, I can sketch a curve passing smoothly through these 3 points and meeting these asymptotically. So, this will be a very good approximation to the variation of gain corresponding to a pole. Now, as I said, we just do not have one pole or one zero, but we have maybe several poles and several zeros, and so we have to combine the effects of all the poles and all the zeros. And as we saw, the log to the taking the logarithms simplifies our life by requiring us only to add and subtract, but we can go one step further. Am I going to draw all these separate curves and then am I going to add them just as you could in coordinate geometry and early work on sketching of curves? You perhaps did it by drawing 2 separate curves and then adding their ordinates to get their sum. Now, that is of course one way of doing it, but in this case the approximations are so simple And what is the nature of the approximation? Horizontal line towards the low frequency end and a sloping line towards the high frequency end. The slope is 20 dB per decade positive or 20 dB per decade negative, and the corner is at a corresponding corner frequency which corresponds to the location of the pole or 0. So with this much information, one can see that it is not necessary to plot these separate curves, but we can add them up sort of visually and mentally and obtain the resultant graph. Now this will require practice, and obviously I am not going to do it here. So I will ask you to look up any problem in your textbook. In fact, I will put down one problem, and what I will do is I am not going to work out the whole thing in detail. I am not going to calculate the DC gain, etc., etc. I am just going to show you the highlights of what is the result. So let us take a simple example. So let us take a transfer function which say looks like, and let me put a nice simple factor in front, let us say 10, and let me have a say a 0, and the 0 is let us say located at -1. So 10 into s plus 1 divided by, and suppose I have two poles. Let us say there is a pole at 5, so I have s plus 5, and let us say I have another pole at -10. This is a pole at -5, not plus 5. So there is a pole in the left half plane at -5, there is a pole in the left half plane at -10, there is a 0 in the left half plane at -1, and there is an overall multiplying factor of 10. Let us say this is my transfer function. So this is my Gs, and now I want to find out the frequency response, that is I replace G s by j omega corresponding to a sinusoidal input of angular velocity or corresponding to a frequency omega equal to 2 pi f, where f is the Hertz frequency. I want to look at the modulus and angle or argument, and once again I am going to look at the dB counterpart of this, that is 20 log to the base 10 of this. So 20 log to the base 10 of absolute value of G j omega. We will look at that first, and then of course we will look at the angle of G j omega. And we want to find out and draw or sketch a good approximation to this as a function of omega, and we are going to use a logarithmic scale for omega, that is we are going to use a semi-logarithmic paper. Equal increments along the horizontal axis will not correspond to equal increments of omega, but will correspond to equal multiples of omega. And as I showed you earlier, usually you have decade sections of the semi-logarithmic graph paper. So it could be labeled omega equal to 0.1, omega equal to 1, omega equal to 10, etc., etc. So let us do that here. Now if I look at this, I see that there is a 0 at -1, and if I were to have this only, then there will be a corner frequency which will be given by the 0 is at -1. So the absolute value of -1 or 1 radians per second. So there will be a corner frequency at 1 radians per second. There is a pole at -5. So there will be, if I just looked at the plot of corresponding to this factor, I would have a plot which would have a corner at 5 radians per second, and the third one corresponds to -10, and so it will have a corner at 10 radians per second. So if I had plotted these three approximations separately, each one of them would have a low frequency asymptote, a high frequency asymptote, a corner frequency. The corner frequency would be different for these three. The corner frequency for this is 1, for this 5, for this 10. The high frequency slopes of all of them are 20 dB per decade for the 0 and -20 dB per decade for the pole. What about omega tends to 0? What happens as omega tends to 0? Now that in fact is very easy to evaluate. You don't really require a lot of effort, because s is going to be replaced by j omega, and then omega is going to be replaced by 0. So you might as well replace s by 0. So if I do that, what do I get? 10 into 1 divided by 5 into 10. So that gives me a DC gain of 1 by 5. So there is a DC gain of 1 by 5. Now remember, I have to convert this into decibels. I don't work with gain, but I work with decibel gain when doing these Bode plots. So what is the dB gain corresponding to this? That is 20 log to the base 10 of 1 by 5. Well, that is -20 log to the base 10 of 5. And what is the logarithm of 5 to the base 10? It's approximately 0.7. because the logarithm of 2 to the base 10 is 0.33010. The logarithm of 5 to the base 10 will be 1 minus that, and therefore it is nearly 0.7. And remember, we are doing approximations. There is no point in writing down the third and fourth place of decimals. 0.7 is good enough. So how much is this? Minus 20 into log of 5 to the base 10, which is 0.7 nearly. So this is approximately equal to minus 14 dB. So the DC gain is going to be approximately minus 14 dB. Now, whether it's a pole or it's a zero, the asymptotic approximation for low frequency, as we have seen earlier, for a zero it is a horizontal line of some value. For a pole, it's again a horizontal line of some value, depending on what? Depending on this pole or zero location, right? So when I add them up at the low frequency end, I am simply going to add these horizontal lines which are at different levels, add or subtract. So I don't really have to do all that. The net effect is I draw a horizontal line at a level of minus 14 dB. So the dB gain will approximate minus 14 dB as omega tends to 0, and horizontal line at that level will be a good approximation. So I can think of sort of starting my DC at the low frequency part of the total approximation at a level of minus 14 dB. Now what is going to happen after this? So think of sort of moving along the omega line. Now there are three corner frequencies. There is one corner frequency at 1, there is another corner frequency at 5, and there is a third corner frequency of 10. So as you start increasing omega, and remember we don't increase omega from 0, we increase it from some low value like say 0.1 hertz or 1 hertz and so on. Where should we start? Well, the three corner frequencies are 1, 5 and 10. So we should start at a value lower than 1. So maybe we can start at 0.1. Where should we end, or how far should we go? The highest is 10, so perhaps we should go up to 100. And therefore, when we are going to do this plot, we will choose the semi-logarithmic paper, and the frequency range or the range of omega will be from 0.1 radians per second to 10 radians per second, right? Or no, one decade above the 10 radians, so 0.1 to 100, which is how many decades? 0.1 to 1 is 1 decade, 1 to 10 is the second decade, and 10 to 100 is the third decade. So there are 3 decades. There is change in frequency by a factor of 10 raised to 3, 10 times 10 times 10. And therefore, on the graph paper, I will have 3 cycles. So if I just show that for the moment without showing all the details, well, here is this say 0.1, here is 1, here is 10, and here is 100. If this was an ordinary graph on an ordinary paper, this would not be correct, because the distance between 1 and 10 seems to be the same as the distance between the point corresponding to 10 and 100. But this 1 stands for omega, but what we are plotting horizontally is log to the base 10 of omega, which of course we are not showing here. But if I did want to do it, then I could write here u equal to 0, and this is omega equal to 1, omega equal to 10, and therefore u equal to 1, omega equal to 100, so u equal to 2, and omega equal to 0.1, so u equal to minus 1. Now if I don't look at w, but if I only look at u, then it's correct. 0 to 1, 1 to 2, minus 1 to 1, equal increments. So uniform scale for u, but it's a non-uniform logarithmic scale for omega. So I'll choose 3 cycles on the semi-logarithmic paper. And so if I draw the vertical lines, then this is what it is going to be like. So omega equal to 0.1, 1, 10 and 100. And as I told you earlier, and I hope you have procured for yourself a semi-logarithmic paper and are looking at it side by side, if this is 1, let's say, then where will the point 2 be? It will not be midway, because omega equal to 1 and omega equal to 10 is what these 2 points are. It will be at a distance of 0.3, because log to the base 10 of 2 is 0.3. So here will be the frequency corresponding to 2 roughly. So here will be the vertical line corresponding to 2, the next frequency. Then there will be 3, then 4 and so on, and it gets crowded as you go towards the right. Then you are at 10, So 20 is again 1/3, almost 1/3 the distance away. So here is the line for omega equal to 20, then 30, 40 and so on. Or if it is 0.1 here, here is 0.2, 0.3 and so on. Okay. So you have to take the semi-log paper and then make markings on it like this, corresponding to omega equal to 0.1, 1, 10 and 100. One does not usually even write omega. It is understood that it is omega which is being shown logarithmically along the horizontal axis. And then we have to choose the vertical location of our graph, because all we have on the graph paper are simply equally spaced lines, lines which are equally spaced vertically. They may be 1 centimeter, the major lines may be 1 centimeter apart, or depending on what kind of paper you have at a closer or greater distance. So that does not matter. Now where do I put my 0 dB line, where do I put my 10 dB line, 20 dB line, minus 10, minus 20? That is again something one has to decide, and usually therefore what one does is one goes through this exercise sort of quickly, almost mentally, or just putting down some numbers before actually starting to draw the asymptotic Bode plot. So this is what we will do now. Our transfer function is 10 into s plus 1, that is there is a 0 at minus 1, divided by s plus 5, a 0 at pole at minus 5 rather, s plus 10, therefore another pole at minus 10. Remember, the approximation for 0 is horizontal towards the 0 end, omega tending to 0 end, and it's a line with a positive slope at the high frequency end. The approximation for a pole, because it is a factor in the denominator, is again horizontal at the omega equal to 0 or towards the omega equal to 0 end, and a line with negative slope for the high frequency end. So now you start thinking of it as follows. Suppose I look at a frequency which is small. How small? Well, the corner frequencies are 1, 5 and 10. So if I take a frequency of say 0.1 radians per second, then that's quite small compared with 1. It's 1 decade below the smallest corner frequency. Alright, now for that frequency, what are the three approximations? What is the approximation corresponding to the 0 and corresponding to the 2 poles? You can immediately see that S is going to be put equal to 0 literally, and therefore the DC gain that we had calculated is a good approximation, which takes care of the effect of all the three, the poles, 2 poles as well as the 0. So the DC gain end will be minus 14 dB. Now I think of increasing omega as it were slowly, so I am starting to move to the right from omega equal to 0.1. Now all the three curves are horizontal till their corner frequency. So this curve corresponding to s plus 1 is horizontal till the corner frequency of 1. The other curve s plus 5 corresponding to s plus 5 is also horizontal till that corner frequency. The third one is also horizontal. So up to the lowest corner frequency 1, all the three curves are horizontal. So if I add them up, I will get a horizontal line, right? Therefore the net effect will be somewhat like this. Now I am not putting down the axis right now, I will do that later. So it will be like I had a constant value of gain of minus 14 dBs up to the time that I reach the first corner frequency. So I am now considering increasing omega or increasing log to the base 10 of omega if you wish. Now when I reach the first corner frequency, which is corresponding to this 0, then this has an approximation which is no longer constant but which increases with frequency. The other two are however below their corner frequencies, and therefore they are as good as being constants. So what is the net effect? The 0 contributes an increase in gain, the 2 poles are yet to make any significant difference. Therefore the net result is an increase in gain. An increase in gain at what rate, so to speak? 20 dB per decade. And so if this was the curve so far up to the corner frequency of 1, then from here it will start growing at the rate of 20 dB per decade. So one shows it, or one thinks of it like this. Now will it keep on growing indefinitely? It would if this was the only factor, but then there are the 2 poles. So what is going to happen? As we increase the frequency further, you reach the second corner frequency 5. So, when you reach the second corner frequency 5, the effect of this pole will start coming into the picture. In other words, the gain will now start decreasing, or this will contribute a decrease in gain, and at what rate? Minus 20 dB per decade. So, let us say here is the point corresponding to 5 radians per second. Up to this frequency there was this increase at the rate of 20 dB per decade. Beyond that frequency, of course, the effect of the 0 will cause the increase at 20 dB per decade, but we have the pole also whose effect is now to be seen, and that effect is at the rate of minus 20 dB per decade. So, what is the net result? And this is where our engineering judgment comes into play. If something is increasing, one part is increasing at 20 dB per decade, another part is decreasing at 20 dB per decade, then what will happen to the sum? The sum will be very nearly constant. So, the net result is a horizontal line from 5 rad per second onwards, but will it continue indefinitely? No. Why? Because the second pole will play its role, starting with what frequency? Starting with its corner frequency, which is 10 hertz. Now, if I show it on this scale, then because it is logarithmic, 1 and 5, so 10 may be say somewhere here. So, up to this point this is a good approximation. Now, beyond this point 10, the 0 of course has its own contribution, the first pole makes its own contribution. So, these two will cancel as they did earlier, but the pole at 10 will now make one more contribution, and therefore, there will be a decrease in the gain at the rate of minus 20 dB per decade. And here also it is horizontal, but one can emphasize it by showing 0 dB per decade. And so, this is going to be a fairly good approximation to the variation of dB gain with frequency. Now, this is an approximation, one can improve it a little bit, and in practice one really does not bother too much to increase it, because here for example this is the first corner frequency, I will have to go 3 dB above, but then here this is the corner frequency of the pole, so I will have to go 3 dB below, but the contribution of the 0 may not be quite negligible. So, I have to add and subtract, and it is not really worth doing it. This horizontal at the level of minus 14 dBs, vertical or not vertical, rather sloping at 20 dB per decade, positive slope up to corner frequency of 5, then horizontal again up to the corner frequency of 10, and then finally sloping downwards at minus 20 dB per decade is a good approximation. Now, I said that we have to do it on the graph paper. So, where do we choose the 0 dB line and so on? Where should we choose it? Well, again some quick calculations and approximations which one can make quickly are enough. Here it is minus 14 dBs. So, on my graph paper I must be able to show this line minus 14 dBs somewhere. What about this point? I can quickly calculate the approximate gain corresponding to this frequency. Why? It is minus 14 here, the slope is 20 dB per decade. What is this change here from 1 to 5? 1 to 5 is logarithm to the base 10 of 5, that is 0.7 multiplied by 20. So, that is a change of 14. This is minus 14. So, what will be the gain corresponding to this level? It will be 0 dB. So, this point will be at 0 dB level. Then of course, this point is at 0 dB level. So, at frequency of 10 radians per second, the total gain will be roughly 0 dBs. That means the gain will be just 1, absolute gain will be 1, or there is no gain, there is no loss, there is no gain, there is no attenuation. Subsequently, what is going to happen? There is going to be decrease at the rate of 0.20 dB per decade. So, if this is 10, then I will have the 0.100 for that frequency, 100 rad per second. What will be the net decrease? 0 here, a decrease of 20. So, this level will be minus 20. Now, if my range of interest goes beyond 100, then I will have to make provision for it. Similarly, if I am interested in frequencies much less than the first frequency that we started off, namely 0.1, then I will have to provide for it on the graph paper. But what is the change in gain for this frequency range of interest? Let us say 1 decade below the lowest corner frequency, 1 decade above the highest corner frequency, and this is what one usually does. For this point at the low frequency end, it is minus 14 dBs. then it is increasing going to 0, and then it is decreasing, and by the time I have reached 100 radians per second, it is nearly minus 20. So, along the vertical direction, I must make a provision of variation from minus 14 dBs to 0 dBs to minus 20 dB. Along the horizontal, I must make a provision of 0.1 radians per second, 1, 10 and 100. Now, with this kind of a qualitative work done, one is then ready to use the semi-logarithmic paper. In fact, it is not even necessary to use the semi-logarithmic paper, although as an engineer one should make use of such a paper as far as possible. So, if I show it now, it will be something like this. I have my vertical level which ranges between minus 14, 0 and minus 20. So, I may allow maybe 10 dBs in the positive direction, although I am not likely to use it. In the negative direction, I have minus 20, but I may go up to say minus 30. So, the vertical variation, the graph paper scale that I will choose will be from say 10 dB to minus 30 dB. So, 10 dB, 0 dB, minus 10, minus 20, minus 30. So, let us say here is the 10 dB line, then I will have what, 0 dB, minus 10, minus 20, minus 30. So, here is the 0 dB line, here is the minus 10, minus 20 and minus 30 line. I have to choose the vertical scale appropriately depending on the width of the graph paper that I have, the height and the width of the graph paper. I am not going above 10, I am not going below minus 30. So, this is adequate. So, appropriate scale has to be chosen. For the horizontal axis, I have already chosen, because of the frequencies, 3 decades. So, here is let us say one decade, end of the decade starting at 0.1, and here is the next one, the second one, and here is the third one. So, this is 0.1, this is 1.0 rad per second, this is 10.0 rad per second, this is 100.0 rad per second. Because I do not really have to write 0.0, but this is just to make sure that I have written the number correctly. Now, where do I start? At the low frequency end at 0.1, and even up to 1, the approximation was minus 14 dBs. So, here is this minus 14 dB line. Then from here, and of course, here is the vertical line corresponding to 5 rad per second, and we found out that the net gain at that point is going to be 0. So, this is the upward sloping line with 20 dB per decade. Minus 14 has become 0 here, because in terms of decade we have gone 0.7 of a decade. So, 20 times 0.7 is 40. Then we have this horizontal portion from over this range from 5 to 10, because the 0 contribution has cancelled the pole contribution, and then beyond that from 10 to 100 there is a drop of 20. So, here is the curve, and then of course it goes beyond. So, this is the approximation to the variation of gain with frequency, and this is what Bode's contribution was, that without going through actual detailed numerical calculations, you can get a good idea of what the variation of gain with frequency is going to be like. This was his contribution, and this is the importance of Bode plots, not actually evaluating the gains at various frequencies and joining them by a nice and smooth curve. That is not worth it, because as we saw in the Nyquist criterion, you do not really need the full polar plot at each and every point. Experimentally also you do not really get a full plot. What you get is gain at a number of frequencies and phase shift at the same set of frequencies. What you want is the qualitative kind of information which is therefore available here, and this is the main idea behind the Bode plot. So, I hope you will be able to work out problems where the poles and zeros have different locations, and there may be several zeros and there will be several poles, and the multiplying factor in front may not be 10, but it may be something else. Now, there are one or two things which one can remember, and in some books it is done one way, in some books it may be done the other way. I have written a factor like s plus 1 either in the numerator or in the denominator, and I have talked about a 0 or a pole at minus 1. But as we saw earlier, this has something to do with the transient response and the time constant of the transient response. So, instead of writing s minus z or s minus p, one can write it in the form of tau s plus 1, or this tau, although it is a time constant, there will be a minus sign here, it will be of the form minus tau s plus 1. If something is in the left half plane, it will be like this with tau positive. If something is in the right half plane, it will be like this with tau positive. Now, when you do this, tau is not the corner frequency. What is the corner frequency then? You have to go to this form, s minus z or s minus p form. So, the corner frequency corresponding to this will be 1 by tau. 1 divided by the time constant, that is the reciprocal of the time constant, is the corner frequency. So, if you write the transfer function in this form, then the coefficient of s is not the corner frequency, but the reciprocal of it is the corner frequency. There is one advantage in writing it in this form, because when I write it in the form tau s plus 1, when I put s equal to 0, what remains? Only 1. So, the tau just disappears and I have 1, 1, 1 for each of the poles and zeros, only the overall multiplying factor is what remains. So, the DC gain is very easy to figure out, but I do not think you will consider yourself unable to figure out the DC gain in a case like this. That is, you can't put s equal to 0 mentally and see that what you have is 10 into 1 divided by 5 into 10 or 1 by 5. But it is sometimes advantageous to show the time constants explicitly, because ultimately they tell you what the transient response is going to be like. So, if your expression has factors of this form, remember that this tau is not the corner frequency. 1 divided by tau, or if it has a negative sign here, then of course take the positive part, and 1 divided by that is the corner frequency. And when you are looking at the DC gain, then of course ignore the tau altogether and ignore this ones, because they are just multiplying and dividing, adding to or amounting to 1. So, that is one thing. The second thing is that we have only looked at real poles and real zeros. What if the poles are not real, but then as we know they occur in complex conjugate pairs, or they occur in conjugate pairs. And for example, on the pole 0 diagram, there may be a pole here, there may be a pole here, then this may be say minus 1 plus j1, and this is a pole minus 1 minus j1. What about the frequency response corresponding to a pair of poles like this? Now, it is not very difficult to get an idea of what it is going to be, and again we are interested not in the exact calculations, but good approximations. So, once again one can look at omega tends to 0 and omega tends to infinity situation, and then one will see that there again we will get exactly two asymptotes, a low frequency asymptote and a high frequency asymptote. And to see what it is, let us take this example and complete the job. So, there is a pole here, so corresponding to this there is a factor s plus 1 minus j1, corresponding to this there is a factor s plus 1 plus j1, and so what really I have, if I want to get rid of the complex numbers, is the factor s plus 1 minus j1 into s plus 1 plus j1, and one can see immediately that this is s plus 1 square plus 1 square. And this will remind you of the form in which we wrote the quadratic expression when the factors were not real, or alternately we wrote it as s squared plus as plus b. So, instead of looking at the poles or zeros in their complex form, look at the quadratic expression like this, s squared plus as plus b. Now, replace s by j omega, okay, we do that, what do we get? And then consider the case when omega tends to 0 and omega tends to infinity. What about omega tends to 0? It is very easy to see that this simply amounts to b. So, at the DC end we will again have a constant gain given by this number b, or 20 log to the base 10 of b, or minus 20 log to the base 10 of b, depending on whether we have the numerator, that is 0, or denominator. So, that is taken care of. So, the DC asymptote is going to be a horizontal line. What about the high frequency asymptote? Now, if you replace s by j omega, you will see that you will get a omega square from here, you will get a omega from here, and this is of course a constant. So, for large omega you can forget about the omega and you can forget about the constant, and what remains is only omega square, and therefore we have 20 log to the base 10. If you have s squared, absolute value of omega square, or minus omega square if you wish. So, this is what? This is 40 log to the base 10 of omega. So, instead of 20 log to the base 10 of omega, I have 40 log to the base 10 of omega. So, the high frequency asymptote has a slope of 40 dB per decade rather than 20 dB per decade, or minus 40 dB per decade rather than minus 20 dB per decade. And that is not very difficult to remember, because we are looking at a pair of complex poles. We are looking at the effect of not one pole, but of two poles together, or of not one zero, but two zeros together. So, earlier each pole or zero contributed minus 20 or 20 dB per decade. Now, we are considering them in complex conjugate pairs. So, the contribution will have a slope of 40 dB per decade for a zero pair of zeros and minus 40 dB decade for a pair of poles. So, that is one thing that is to remember. But the second thing is, what about the actual curve and the asymptotic curve? What is the difference between the two? Now, there is something that one has to take a little bit of care of, and some little computation may be necessary. So, we will take a look at that next.